In previous class, we have seen the background is nothing but the peaks associated with impurities which are present in our analyte, isn't it? And because of that, the featureless and the unstructured spectrum, due to presence of impurities superimposed on a spectrum of an analyte, is called the background. And so it's difficult to judge which peak is of our analyte, whatever we are analyzing, or whether our analyte peak is interfering with impurity peak. Maybe that impurity is from solvent, or maybe any other impurity while adding or while taking sample for processing. So that kind of analysis or that kind of peak we can avoid, or we can find out with the help of both the techniques, difference as well as derivative, isn't it? So the correct answer for this question is both. Difference as well as derivative spectrometry makes an important role, and whatever the background absorption gets created on spectra, that can be eliminated. So that is a takeaway from this poll. Now we will talk about derivative spectrometry, what it is exactly, or what is the importance of derivative spectrometry. And before that, or before start this particular derivative spectrometry, it's very important to understand why derivatization is required, or why we are moving from normal UV absorption to derivatized form of absorption, or maybe the derivatized spectrometry. So before that, you just give me one answer over here in a chat box. Whatever UV spectra is there, or whatever output is there of UV spectra, so whatever the graphical output we are recording, so what will be on x-axis and y-axis, or maybe which are the parameters, what versus what? That is a basic question I am asking over here in a chat box. So what parameters, or which particular pointer we will consider to record, or maybe the UV spectra, when we are going for lambda max absorption of any compound, or to find out lambda max of a compound? What is the graphical output, what versus what? So I'm expecting your answer in chat box. On x-axis, now Surbi has written, Saurabh has written, Yadav Saurabh, that is absorbance versus wavelength. Yes, Nazia has also reflected same answer, absorbance versus wavelength. So absorbance versus wavelength is the correct answer, and we record, or we will get output to find out lambda max of a given compound on this graph, absorbance versus wavelength. So derivatized form means what, or why derivatization is required? So first thing you should consider, or first thing you should keep in mind, that derivative spectrometry is a very commonly used technique for the background correction. Now question will ask, why you are going for derivatization of spectra? The correct answer is what? It is generally used for the background correction. And you know what is the meaning of background? That is peaks associated with impurities. And for the selective analysis of compounds producing overlapping bands in their UV spectra when present in a mixture. Whenever we are analyzing our mixture by using UV visible spectrophotometer, at that time, whatever the graph you are mentioning in a chat box, absorbance versus wavelength, so we will get analyte peak, along with analyte peak some impurities peaks, also gets reflect. So this derivative spectroscopy or spectrometry technique is used for background correction. So in what way this technique is helpful to correct background effect? So that is our today's uh, takeaway from lecture. So in derivative spectrometry, a mathematical derivative of the absorbance with respect to the wavelength of radiation is calculated by the instrument itself, isn't it? We are mentioning graphical output is absorbance versus wavelength, but when we are going for derivatized one, we will get a mathematical derivative of the absorbance with respect to the wavelength of radiation, and this is calculated by instrument itself, whatever the software we are using, based on which kind of instrument, UV visible spectrophotometer we are using. According to that software only calculates derivatized form of absorbance with respect to the wavelength and give multiple recording of absorbance versus wavelength. And a spectrometer can calculate different orders of derivatives, isn't it? So for our understanding purpose, we are considering the normal spectrum. So normal spectrum is what? Whatever you are reflecting here on a graph, that is absorbance versus wavelength. So that is a normal spectrum. And to understand this normal spectrum, we will consider it as a zero order spectrum, isn't it? So again here I will share screen so that based on whatever graph you will observe, your concept will get clear. So I just stop sharing of whatever poll results and I share one image so that you will understand exactly what is derivative spectrometry. So if you observe over here, are you getting screen, students? Are you able to see exact graph over here?
Yes, sir.
Yes, sir.
Yes. Yeah, good. So if you see what we are mentioning, or this figure reflects, again this figure is from Supriya Mahajan book only. Whatever about derivative spectrometry is there. So you will get this figure over there. So here, if you are considering normal spectrum absorbance versus wavelength, so this is a, for example, one peak we are getting, isn't it? This is a normal scan of given compound or whatever we are analyzing on spectrophotometer. So that's why we are mentioning it as a 0D or maybe one peak or maybe normal spectrum, zero order spectrum. And this is a simple plot of absorbance versus wavelength. So whatever the lambda max is there, maximum amount of radiation is getting absorbed at whatever wavelength, that is called as a lambda max. So this is a scan of our analyte, and we will consider as this graph is a normal graph or maybe zero order graph or zero order spectrum. So obviously when we are moving from zero order to first order spectrum, so what will happen now? Derivatization, see in what way we are connecting this derivatization concept by observing normal spectrum first, and then we are talking about first order spectrum. First order spectrum, what it is exactly? It is obtained by calculating the first order derivative of an absorbance. First order derivative of an absorbance with respect to wavelength, so as to get the ratio of dA or derivatization of absorbance divided by derivatization of wavelength, and is represented as a 1D, and it is a plot of dA divided by d lambda versus wavelength, isn't it? Or I just write some points over here so that again you will get clarity on normal spectra or derivatization spectra. Suppose we are taking first derivative of absorbance, isn't it? So what it is exactly, how it will obtain first derivative? Suppose I am writing over here one point, isn't it? So I will just reduce font size of this, and if you see, it is obtained by calculating the first order derivative of an absorbance with respect to the wavelength so as to get the ratio of what ratio? dA divided by what kind of ratio you will get? Suppose I am again using another page over here, and I will just paste over here. This is it. So I will just increase the font size for your understanding. So it is obtained by calculating the first order derivative of an absorbance with respect to the wavelength so as to get the ratio of this dA divided by d lambda, or maybe the derivatization of absorbance divided by derivatization of wavelength, and it is represented by 1d. So obviously it is a graph of dA by d lambda versus wavelength. So this is a first order spectrum as you are observing over here, isn't it? For example, this is a first order 1d, dA divided by d lambda. So what is your observation over here in this graph? Here you are getting two peaks, isn't it? So what is the splitting pattern of this peak? That is a point of discussion that we will see. But before that, we will try to understand what is a zero order, what is a first order, what is a second order, what is a third order spectrum. So is it clear what is a first order spectrum for all of you? Yes? Any doubt over here? It is dA by d lambda versus wavelength, or this is the 1d. Now just don't give thought about what is a splitting pattern, isn't it? That we will reserve for some time, and we will open up that question also, or maybe we will explore that answer also after some time. So this is the 1d. So obviously, what will be the second order spectrum then? Can anyone answer? Now this is the zero order. Now this is the 1d. Now can anyone answer about what will be second order spectrum, or maybe the second order derivatization? It is obtained by calculating the, yes,
Sir, it may have three peaks.
it may have three peaks. And what will be the graphical output? What will be on x-axis and what will be on y-axis? So if you,
D2A by D lambda.
yes, very good. So this is the 2D. So d2a divided by d lambda square, and we are getting three peaks over here, isn't it? In first order derivative, two peaks. In second order derivative, that is three peaks. So graphical output is same, d2a divided by d lambda square. Again we will move further. Third order spectrum. So in third order spectrum, it is obtained by calculating the third order derivative of an absorbance with respect to wavelength. So to get the ratio of d3a divided by d lambda cube, isn't it? So here in third order spectrum, if you see splitting pattern over here, so number of peaks are 1, 2, 3 and 4. 4 peaks we are getting over here, isn't it, in third order spectrum. Again we will move further. Fourth order derivative. See, we have started from this normal spectrum. This is only a single peak. Then we have scanned for first derivatization, then second derivatization, then third derivatization, and this is now fourth derivatization. So here, if you observe splitting pattern, that is d4a divided by d lambda raised to 4, we are getting 5 peaks. So this is the first, second, third, fourth, and fifth. So what is the trend over here, or whatever you are observing in this graph? What is the takeaway from this? Based on derivatization, this peak is getting split, isn't it? In what fashion? That is n plus 1, isn't it? For example, zero order hai, so one peak we are getting. First order hai, so when we are considering as a first order, so we are considering as a, for example, small n, isn't it? Plus 1. So what you are observing over here? First order plus 1. So obviously 2 peaks. When we are moving further over here, that is a second order. So we are getting n plus 1, that is 3 peaks. Again 4 peak. Then 5 peaks as a fourth order derivative of absorbance. So we can take 6, 7, 8, 9 till all the background gets over or gets corrected. So this is the n plus 1. This is a splitting pattern, isn't it? So the nature of all the spectra, as you are observed in a graph. So what are the characteristics of whatever the image we have seen? How will you give some reflection on this image? The first point is that in derivatized spectra, maxima and minima of the original function, isn't it? This is the maximum value, and the minimum of the original function take zero values, isn't it? For example, this is the maximum value. So this maximum value in a first order derivatization has taken zero value over here, isn't it? This peak, and this peak gets split as a peak number 1 and peak number 2. So this is a one major observation in derivatized. So in derivatized spectra, maxima and minima of the original function take zero values, and inflections are converted into maxima or minima. Example, what is same over here? The first order derivative spectrum takes zero value, isn't it here? At the maximum of the zero order spectrum. This is a zero order spectrum. So obviously here the zero value has started over here, and the inflections we are getting like this. So that is the splitting pattern n plus 1. Another observation we can make out that derivative spectra are more structured, isn't it? You will get clear cut specifications or clear cut differentiation, more structured than the original spectra. Since the number of peaks goes on increasing with the increase in the order of derivative, isn't it? Now we have seen number of peaks are increasing if we are moving from first order, second order, third order, and fourth order. So number of peaks are increasing. In the first order derivative spectrum, the original band, this band gets splits into two. In a second order derivative spectrum, the original band splits into 3. Again, the number of peaks in a spectrum of order n would be this, n plus 1 will be the splitting pattern. This is another observation. Though the increase in the number of peaks helps in producing the spectral characteristics of a compound, that also increases the complexity, isn't it? If you are going for number of derivatives, the number of peaks you will get, and you will get more complex spectra. So in this way, derivatized spectra work to identify very minute differences between structure. And it is most widely used order of derivative spectra are the, means whenever we are doing analysis, So in majority of analysis, if you see any research paper, at that time when there is a difficulty to understand analyte peak as compared to background, at that time max to max second order derivative and the fourth order derivative means till fourth order. Generally, analysts scan the compound till fourth order and try to find out the interference due to the background, isn't it? So this application we can put, or what will be the major application of this derivative spectra? We can take case study, isn't it? So that is, we can record the zero and second order spectra of amphetamine and phenylethylamine. These are the two different drugs. So if you see structure of these two drugs, again one image you will see over here. So if you observe this image now, I just reduce size of this image. Amphetamine and phenylethylamine, isn't it? These are the two drugs. If you see the structure of these two drugs, amphetamine is CH2, CH3, NH2 is there, and phenylethylamine is CH2, CH2, NH2 is there. So when we will scan this compound at a zero order spectrum or normal spectrum, though both these compounds will give us somewhat similar pattern as a lambda max value or maybe the spectra. If you see over here, zero order spectrum of amphetamine and phenylethylamine. So this is a such kind of peak we get on a spectra, isn't it? And we have already seen that in a derivative spectrometry, a single peak corresponding to the zero order splits into more peaks as the order increases. And hence the derivative spectra are more structured than the zero order spectra. And this splitting pattern is slightly different for different compounds and is a characteristics of that substance. For example, if we are scan amphetamine with second or third order derivative, or maybe the phenylethylamine by second or third derivative, obviously they will derivatize in a different fashion. In a zero order spectrum, it is difficult to identify exactly this peak is of amphetamine or phenylethylamine. But when you scan these compounds by using derivative, at that time you will realize no, there is a structural difference, and that structural difference will get reflected on graph derivatized spectra. So from the splitting pattern, one can identify a compound, isn't it? So you can easily correlate. That is, the zero order spectra of amphetamine and phenylethylamine are almost identical, isn't it? This is the zero order spectra. So that one cannot identify whether it is a amphetamine or phenylethylamine. So the second derivative spectra of two are also very similar. If you talk about this second derivative spectrum of amphetamine, and this is a second derivative spectrum of phenylethylamine, isn't it? If you see the pattern over here, this is the dot and this is the another dot. So this peak or whatever the peak size is there, that is equal over here in a phenylethylamine, and in amphetamine it is somewhat lower side as compared to the second peak, isn't it? So the second derivative spectra of two are also very similar, but the intensity ratios of certain side maxima have a characteristic differences. So these are the intensity of line, isn't it? Or intensity of spectra, whatever the peak we are observing. So here intensity is more of both the peaks, or this peak is equally intense with first peak. But in amphetamine, this peak is somewhat less intense as compared to this. And this is a one of the major application of derivative spectroscopy in pharmaceutical analysis. So this difference is made use of in the identification of individual compounds. So obviously in this way we can use derivative spectroscopy in our day-to-day analysis to identify or to control the background impurity. So this is a major application of derivatized spectra. Clear this thing? Any doubt over here, dear students? Yes, are you getting clarity
Yes.
on this particular point?
Yes, sir.
Good. Now just put another heading in your notebook or whatever the notes you are taking, if any. Another technique name is about difference derivative or difference derivative spectrometry. So if I write title over here, difference derivative spectrometry. So difference derivative spectrometry and derivative spectroscopy. Now you got a clarity about derivatization, isn't it? Now we will talk about difference derivative spectrometry. What it is exactly. So can anyone guess what will be difference between this derivative spectroscopy and difference derivative spectrometry? Can anyone talk about this particular point? Now, see, you know what is a derivative one, isn't it? We are taking derivatization from first order, second order, third order, fourth order, and based on that, peak gets split as a n plus one rule. So, what is a difference derivative then? Can anybody talk? Or maybe you can compare with normal colorimetric or UV spectroscopic analysis and or maybe the colorimetric analysis. Now we have done experiments in a previous session, colorimetry of salicylic acid, colorimetric estimation of salicylic acid, or maybe we used what we did a assay of various tablets. So what is a difference you will observe in a normal UV or colorimetric procedures? How will you scan? For example, I'm just writing over here as a normal UV analysis, isn't it? Or maybe colorimetric. And what is a basic observation when we carry out experiments on colorimeter or normal UV method? The reference and the test solutions are prepared, isn't it? If you see the reference and test solution, we are preparing a reference solution, maybe the blank solution, and the test solution we are preparing of our analyte. And these are prepared exactly in the same manner, isn't it? The only difference being that, what is the difference? Can anybody talk about this difference? What is the difference between reference and test solution? This is the reference and this is test. So can anybody talk about difference between these two when we are analyzing compound by using UV spectrophotometry? Yes. Can I ask this question to Arushi or maybe Vinita? Can you unmute yourself and answer this question? Vinita or Arushi? Anyone? Or maybe Jyoti, Sony, or maybe Surbi Sony? Anyone?
So the
Yes.
reference and test solution might differ into concentration wise.
Hmm. No, try to just recollect experiments on salicylic acid experiment we did, or maybe assay of aspirin tablet or paracetamol tablet by using UV visible spectrophotometer. So we use blank solution and test solution, isn't it? So what is a blank and test difference?
So
Yes.
drug. presence of drug.
Yes, yes, yes.
Analyte presence.
Yeah, very well. So the reference solution doesn't contain analyte, isn't it? Or whatever we are analyzing. अगर paracetamol कर रहे हैं हम लोग, so we are not taking paracetamol in that solution. We are taking only the solvent in which our drug is soluble or using for our UV analysis. And test solution is showing the analyte. Isn't it? This is a major difference. So that the reference solution doesn't contain an analyte, and this increases the selectivity of the measurements of the absorbance of an analyte by decreasing or eliminating the effect of absorption by the solvent and the other reagents, or by maybe the impurities present therein. Isn't it? And when we will scan this compound, so easily we can observe the peak of blank solution or atto zero we are doing, and we will measure the absorbance of our analyte or the test solution on a spectra against blank. So in this way, this increases the selectivity of the measurements of the absorbance of an analyte, whatever we are using in a test solution. By what way? By decreasing or eliminating the effect of absorption by the solvent. Only here as a plain solvent in a reference solution or test solution, or maybe other reagents, or maybe other impurities associated with the same. Whereas now this is a normal or UV colorimetric procedure, whatever we have done, or you experience these things. Now we will move over here on this difference spectrometry. Suppose I am talking about this difference spectrometry. So in difference spectrometry, two solutions are used, isn't it? Here also two solutions are used. In difference also again two solutions are used. I am writing two solutions, both of which contain the same reagents in the same concentrations. See, try to find out exact difference. Same reagents, both the solutions contain the same reagents in the same concentrations. Same concentration. One more point I am writing over here, including an analyte. Are you observing difference between this normal and difference? This is a normal method. And if you see over in a difference, two solutions are there. Here also two solutions are there. But here analyte is not present in a blank or reference. Here analyte. So here in a difference spectrometry, same reagents, same concentrations, including an analyte. So what is the difference then? Can anyone put logic over here? What will be difference spectrometry then? Since an analyte is present in both the solutions, these solutions are not designated as the reference solution and test solutions, isn't it? Here you are observing clear-cut difference. This is a reference, this is a test. Here we are talking about two solutions, so there is no difference. We are mentioning it because it contains both reagents, concentrations of including same analyte. So what is the difference then? Why it is called as a difference spectrometry? Since an analyte is present in both the solutions, these solutions are not designated, isn't it? The difference spectrometry makes use of. Can anybody put keyword over here? That is chemical derivatization. What is happening? Just see, this is a keyword over here. That is chemical derivatization. So what is a chemical derivatization then? Yes. In what way we can do chemical derivatization now in organic chemistry?
Change in pH maybe.
Yes, yes, you are on a correct track. Now in organic chemistry, we have done some experiments. I think maybe I don't know whether you can recollect that experiments or not. In binary mixture analysis, we are considering that this is a derivatized form of compound. So what is that derivatized form, or in what way we can do the chemical derivatization? So whereas the difference derivative spectrometry makes use of chemical as well as mathematical derivatization. When we are talking about difference only, so it is about chemical derivatization, isn't it? I am again see writing over here difference spectrometry, that is about chemical derivatization. And when I am writing over here as a difference derivative, so what will be the keyword over here then? क्या होना चाहिए difference derivative spectrometry? Suppose I am writing over here difference spectrometry means what? Chemical derivatization we are doing. Difference derivative means what? Here we are doing chemical. Yes, anyone can talk over here. Chemical and mathematical. How come? Because in derivative spectroscopy we have just seen this is about derivative, isn't it? We have seen zero order spectra, first order spectra, third order spectra. So what we are doing? Difference derivative spectrometry. Suppose somebody asked you, what is the difference between difference spectrometry and difference derivative spectrometry? In GPAT also such kind of questions will be there. Difference derivative spectroscopy involves, your options will be chemical derivatization, second option will be mathematical derivatization, third will be both. So answer is both chemical as well as mathematical. Suppose question is about what is a difference spectrometry, so only answer is about chemical derivatization. That's all. So in this way, we will try to understand this difference derivative spectrometry, isn't it? So here I am again writing over here either as a difference or maybe derivative or maybe the difference derivative, that is combination. So this you got difference derivative spectrometry. So the simplest chemical derivatization, as you rightly said, that includes change in the pH of the solution. What we can do over here, simplest way to derivatize compound. So you can change the pH, isn't it? pH of solution. The chemical derivatization of an analyte is carried out in one of the solutions, not necessarily the test solution. The difference in the absorbance of the two solutions is recorded and is plotted against the wavelengths. Are you getting? For example, we are going for difference derivative spectroscopy. We are doing chemical derivatization by changing pH of solution. So in normal, you observed reference and test. There was a two clear-cut differentiation. Here, any one solution we can use, isn't it? Any one solution. Out of these two solutions, we can go for any one. We can take any one. For example, two solutions are there, solution X and solution Y. So either you can take X or anywhere, either you can take Y and you will change the pH of this Y solution. For example, we have picked up Y. So we will change the pH of this Y, isn't it? We will not touch this X, that will be remain as it is, but we will derivatize this Y. And what we will do? We will record absorbance of these two solutions on a graph, absorbance versus wavelength, isn't it? And if you are doing this thing, so for example, this is a graph you are getting here on a page in this figure, again picked from Supriya Mahajan book only, that is absorbance versus wavelength, isn't it? So this is the first graph, normal spectrum. So this is the A, isn't it? Wavelength 1 and this is a wavelength 2. So for a case study purpose, we are taking as absorption of phenol. Phenol is there C6H5OH in acidic pH. So this is the acidic pH. This is the A diagram, isn't it? Or maybe the A pattern in this diagram. This is in acidic pH. And B is what? That is in alkaline pH. This particular B. or whatever the peak we are observing over here like this, that is absorption of phenol in alkaline pH, absorption of phenol in a acidic pH. See the difference, isn't it? Here we are getting peak over here we are getting peak over here. Compound is same phenol, but we derivatize or maybe we have scanned that compound in acidic environment and in alkaline environment. Whereas this C picture, if you see over here, that is difference in absorbance, isn't it? That is the delta A, change in absorbance on this axis. So whatever the pattern we are getting over here in this peak, so this is a change in absorbance, that is a A1 at a wavelength 1, whereas change in absorbance 2, isn't it? So this third figure is about difference absorption spectrum of phenol. So this is the difference spectrometry. Now we will talk about this figure, whatever we have just seen over here. Phenols or amines. Now you know the structures. C6H5OH. Suppose I am talking about C6H5OH. This is our phenol. And another point is about RNH2, isn't it? RNH2. I will just increase font size over here. So in this case, C6H5OH and RNH2 in phenol and amine, they shows lone pair of electrons, isn't it? On oxygen, this is the OH, for example. So this is the, for example, I just make it red. And another in case of amine, where will be lone pair of electrons? This nitrogen, isn't it? C6H5OH, and this is the amine in phenol as well as amine. They possess the lone pair of electrons. So these substances interact with acids or bases when we will scan the compound or when we are going for derivatization. So can you think in what way that interaction happens? This will interact with acids or bases, which brings about the changes in the number of lone pair of electrons in them. Isn't it? Whatever the oxygen and nitrogen we are observing over here. So during analysis of phenol by difference spectrometry, now you know what is a difference spectrometry. You will derivatize. Example is, for example, change in pH. When the pH of one of the solutions is increased, how will you increase pH of solution? Yes, anyone? How will you increase pH of solution? Yes, Parth, can you answer? How will you increase pH of solution?
Sir, we can add a alkali or a base.
Yeah. When we are adding base, for example, sodium hydroxide we will add, or maybe the alkalinity, or make it alkaline. So what will happen over here when the pH of one of the solution is increased by adding alkali to it? The number of lone pair of electrons on the oxygen atom increases, isn't it? Whatever the instead of 2, it will become 3. And these electrons are delocalized in this benzene ring, that is the C6H5 ring. So what will happen over here? When delocalization happens, we can observe bathochromic shift. Now, do you remember anything about what is a bathochromic shift? Yes. Bathochromic shift means what? Shikha, are you there? Or maybe Chaitanya? Omkar? Omkar, can you talk about this? Parab Omkar?
Redshift, increasing the wavelength.
Yeah, but what happened exactly in shift? Redshift, you are talking about redshift, but what is exactly shift of absorption means what? What
The absorption maximum is increased. Like increase
Shift of absorption towards longer wavelength or lesser wavelength.
longer wavelength. Is
Very good.
redshift like
Yeah,
bathychromic.
yeah, very good. Yes, Shika, I got your message. You are also there. Anyway, so bathochromic shift is shift of absorption towards longer wavelength, isn't it? So when we are changing pH of solution, so obviously these electrons are delocalized in the benzene ring and hence a bathochromic shift is observed and it will shift towards the longer wavelength. The solution in another sample holder, however, shows the absorbance at shorter wavelength only because you derivatized only one, isn't it? Two solutions are there. You picked up one solution, that is Y solution you picked up over here, isn't it? In this whatever the illustration we have seen, we have changed the pH of this Y solution and we will observe the absorbance of Y with X. So obviously we are getting shift of absorption towards longer wavelength and here it will be remain as it is or maybe towards the lesser wavelength or that difference is there. So what is the output from this then? The solution in another sample holder, however, shows the absorbance at a shorter wavelength only, isn't it? So the shift in the absorption wavelength of phenol with the change in the pH is obviously we are observing over here in this particular graph, isn't it? So in order to obtain the difference absorption spectrum, whatever the difference absorbance we are talking over here, what we are doing, the difference between the absorbance of the solution in a alkaline and the acidic pH is plotted against the wavelengths. So obviously the points A, that is wavelength 1, and point B at a wavelength 2 are the isoabsorptive or isobastic points. So what is the meaning of isoabsorptive or isobastic points? We have done this terminology when we have seen simultaneous equation method. So do you remember what is the isoabsorptive or isobastic points? What it is exactly? At which the absorbance in acidic and the alkaline solutions respectively are same, isn't it? So that is called as the isobastic points. Since the absorbance of phenol is higher in the alkaline pH as compared to that in an acidic pH, the difference in the absorbance at beyond wavelength 2 is positive, but the difference is negative between wavelength 1 and wavelength 2. So that is the difference spectrometry or maybe the difference derivative spectrometry. So with the help of derivatization, we can make out or we can find out the changes in solutions. And according to that, we will try to extract exact absorbance and to find out the exact actual concentration by avoiding the interference of background. So obviously the difference spectrometry can also be used for the selective analysis of compounds from a mixture of a neutral and an acidic or a basic compounds. And when they produce overlapping peaks, a bathochromic shift for an acidic compound makes possible the selective analysis of both the compounds. And if the difference spectrometry doesn't provide the required selectivity, maybe some information we are not getting with the help of plain difference spectrometry by changing only the pH of solution or maybe the derivatization. At that time, the difference derivative spectrometry is undertaken, isn't it? So that will be the, if you are not getting proper answer over here also in a plain difference, then we can take help of derivatization. We will again split peak of our analyte into first order, second order and third order spectra, and we will try to extract the proper information, which involves chemical as well as mathematical derivatization. And so because of the ease of operation, economical methodology and wide application, UV visible spectrometry is a very popularly used technique in the field of analysis as compared to the other spectroscopic techniques. So that is overall content of our today's class. Basically 2 points we have discussed. That is about, first one is about what is a derivative spectrometry only, and second point we have seen difference spectrometry, And third point, that is about difference derivative spectrometry. So takeaway is that you can consider derivative. We will split normal spectrum in a derivatized form into first, second, third order spectra. And in difference, we will talk about what we will say about in difference. Chemical derivatization we will do. And still we are not getting result, then we can take help of both the techniques, that is difference or derivative. And whole output of all these two techniques, difference as well as derivative, is for background correction. Isn't it? One of the advanced techniques to avoid background interference. So this is overall content of our session difference as well as derivative spectrophotometry.